Life appeared almost instantly on Earth, suggesting it's easy.
That was easy.
Yet we see no evidence for it anywhere else in our galaxy, or even in our solar system. Today I'll take you on a deep dive into the math and physical laws behind this fascinating and somewhat disturbing observation. 3.8 billion years ago, in the blink of a cosmic eye after the Earth cooled, life on Earth came about. Either we're astronomically lucky to be first, or we're missing something fundamental about life in the universe. Let's break down the actual numbers. Today I'm going to expand upon themes that Adam Frank discussed in his Lex Fridman podcast interview. Adam Frank is an astrophysicist who's been pivotal in bringing attention to the cosmic perspective of life, emphasizing the interplay between planetary evolution, climate constraints, and the emergence and survival of civilizations. I've had Adam on twice in the podcast. He's a renowned popularizer, professor, and researcher, one of the greats. And Lex Fridman, as you know, just might be the GOAT. He loves to explore everything from cutting-edge robotics to deep scientific questions and even to philosophy, always with a little dose of love sprinkled in. Love you, brother. I've had the honor of being on. Our conversation has 9 million plus views, one of the top 12 or so podcast episodes, and Lex's interviews with astrophysicists always do well. David Kipping has even more, close to 10 million views. So this is a great subject for me to really dive deep upon and share some of my perspective. Now, I'm a cosmologist, not someone who searches for exoplanets like Adam does theoretically, or David Kipping does observationally using tools like the James Webb Space Telescope to dive into the existence of so-called exomoons. But the fundamental question has always puzzled me, as I know it does you. Are we alone?
Extraterrestrials.
It's probably the second most interesting topic one could study after cosmology. Hint, hint, that's what I study. Are we alone? Does advanced life always self-destruct, or can it persist? So I'll break down Adam's main talking points, then I'll move methodically into the underlying equations and data, and I'll do so in a so-called Bayesian framework that I think is unique and possibly controversial, as I don't believe there's a high probability that life exists elsewhere.
Denial.
But I'm willing to be proven wrong. I think that's what a good scientist has to be open to. Adam's conversation laid out several thought-provoking arguments. The first was the proliferation of exoplanets. Adam underlined that only a few decades ago, we didn't even know if other stars had planets. When I started grad school, we hadn't even discovered another planet beyond our solar system. And back then, Pluto was still a planet. Now, thanks to missions like Kepler, TESS, and ground-based radial velocity surveys, we have evidence of billions of planets in our galaxy alone. Many of these lie in the so-called habitable zones, capable, at least in principle, of hosting liquid water on their surfaces. Another topic that Adam highlights in his conversation with Lex and mine, and conversations with me on the Into the Impossible podcast, is the so-called principle of cosmic mediocrity, which echoes the Copernican principle. Adam emphasizes that the notion that the Earth is likely not uniquely favored. And so that would seem to suggest that since life's here and we're not special, there must be life elsewhere. I think that might be a stretch too far. If the conditions that led to Earth's biosphere can be replicated, we may expect multiple experiments in life generation throughout the cosmos. The third point that Adam brings up is so-called civilizational longevity. When we address the so-called Fermi paradox, first proposed by Enrico Fermi during the Manhattan Project, one of the audience members that he proposed it to was the late great Herb York. Now, Herb was my colleague here at UCSD. I actually got to know him. True physicist, and also an advocate for peace. In fact, one of his books is called Making Weapons, Waging Peace, or something like that. I was so delighted to get to know him before he passed away. Now, Adam highlights the planetary constraints that harnessing a large amount of energy can trigger feedback loops like climate change and resource depletion, or even catastrophic pollution. His book, Light of the Stars, talks about how you could use such feedback processes basically to look for the existence of alien civilizations without actually going there.
Life hijacks the planet in a way that the sum total of life creates these feedbacks between the planet and the life, such that it keeps the planet habitable.
In other words, agriculture, climate change, the biosphere is engineered by humans or by organisms at the very least, from the very first microbial life that produced oxygen in the Earth's atmosphere, prior to which there was really only CO2 and other non-life sustaining gases, that is a biosignature.
Atmospheres are the things we can characterize for across 10, 50 light years, and we can see biosignatures, as we're going to talk about. So there is a reason why the habitable zone becomes important for the detection of extrasolar life.
And actually, if you can see that there's global warming that's engineered by, in our case, anthropocentric global warming, that could be used as a technosignature, because even agriculture, as simple as we think it is a form of technology that actually enabled the modern world to exist. So that would be true on other planets, and Adam suggests we could use that as a window to detect or maybe even eventually communicate with other life forms. Now, in the interview, Lex pressed him on his fourth claim, which is whether or not we can actually find unambiguous biosignatures or technosignatures, such as atmospheric disequilibria, industrial pollutants, or unusual spectral lines with the next generation of telescopes, or even the current generation with James Webb Space Telescope. I've had on Nobel laureate John Mather, the project scientist for James Webb, talking about this very subject.
There may be other kinds of principles that actually, because coevolution actually has its own, not deterministic. You're done with determinism, right? Yep. But complex systems have patterns. Complex systems have constraints, and that's actually what we're going to be looking for, are constraints on them.
Now, Frank was cautiously optimistic in this conversation with Lex. Yes, he said, we can place stronger constraints, but only if we remain open to the possibility that life or technology can manifest in multiple ways. Now, what I love about Adam's discussion is that it invites rigorous math-based techno-thinking. And I want to pivot to that to show you how I think about these things. Now, I'm only going to take it on the back of the envelope level. I'm not going to publish the envelope or the napkin, as so many of my colleagues do, but we're going to look at a probability-driven framework, starting with a so-called Bayesian model for life in a multi-planet system. Now, I introduced this to Adam before we chatted early 2024 about his little book of aliens, but I didn't actually proceed to do much more with it until I was stimulated by this wonderful conversation with Lex.
This paper that expands on the Drake equation. What are some interesting things in this paper?
Well, so the main thing we were trying to do with this paper is say, look, we have all of this exoplanet data, right? It's got to be good for something.
So I want to ask the following question. I did mention this on Joe Rogan's podcast as well. Imagine that an astronomer spots two different planets orbiting the same star. Both of them are in that so-called habitable zone of that star. We'll call the first one heat ray. That planet is teeming with biosignatures and even a couple of technosignatures, and we're using the Webb telescope to zoom in on that exoplanet, and we've detected these signals. Now, its companion planet is located, again, within the habitable zone of the star. They're both rocky planets. They both have Earth-like orbits, shall we say. And the other planet is known as SRAM, and the question is, if one of those has a life-giving and life-sustaining technosignature, then what is the probability that we'll see life on the other member of that star, of that binary planet system, SRAM? So this is a very simple probabilistic argument. Okay, now with the Webb telescope, it costs millions of dollars per hour effectively to use the Webb telescope, and you need a lot of hours. So the NASA Time Allocation Board is going to be extremely interested to know that this is likely to be successful. They don't really give it away so easily, as I discussed with my friend David Kipping on our episode of Into the Impossible. So we want to estimate the probability that both planets have life, given that at least one does. Let A, capital A, be the event that both planets have life, and let B be the event at least one planet has life. Let's define a simple per-planet probability of life, which we might imagine to be the fraction of suitably Earth-like worlds that independently develop life. Under the assumption of independence between the two planets, we say that the probability of event A occurring is p to the second power. It's basically independent probabilities. The probability B is basically 1 minus that probability squared. So that comes out to be the quantity 1 minus p to the second power, which, just doing some simple arithmetic, expanding inside the brackets, you get 2p minus p squared. Now, if both planets have life, that certainly implies that at least one of the planets has life. So the so-called probability of p given A equals 1. Now, by Bayes' theorem, the probability that A occurs, that both planets have life, the probability that B has life, given the probability that at least one of the planets has life, we know that to be 1, times the probability that both planets have life on them, which is P of A. Now, that whole quantity gets divided by the probability that B has life. So if you work through this, you get P squared divided by 2P minus P squared. Now, let's pick a concrete example. I like to be numerical. Now, Adam frequently references modestly low probabilities in order to be pessimistic and not be overly optimistic and subject to confirmation bias. So let's say this probability is only 15%. that P equals 15%, therefore, or 0.15. Substituting in, we get the probability that both have life, given that one has life, i.e. Hetrae, the planet Hetrae. The probability that both of these planets have life, given that at least one of them has life on it, is about 8%. That means even knowing the first planet is inhabited, the second planet only has about an 8% chance of also being alive. So this is a stark reminder. Finding life on one planet in a system does not guarantee universal life next door. Now obviously Hetrae is supposed to be Earth, and SRAM is supposed to be Mars, and that's given the fact that life exists on Earth. Mars is essentially in the habitable zone. It's not quite beyond the snow line that Adam talks about, and so it resonates a little bit with the cautious optimism that Adam expresses. Plenty of worlds might have life, but it's not a foregone conclusion that it shows up in every place that meets basic habitability criteria, even when you know life exists just next door. Now let's go a little bit deeper. Let's say that life existed on Earth, and that Earth was the first place that life ever began in our galaxy. This is sort of the most pessimistic variety of life. It still doesn't explain origin of life, OOL, but it does explain perhaps how hard or easy it might be for life to then spread via some process that we'll describe, again, and calculate the odds of finding life off of the Earth. This is sort of a Drake equation where life starts on Earth and then spreads out. Not technological life, not ET life that Drake was interested in, but just life itself. It could be protozoa swimming in an ocean on Enceladus, for example. But let's extend it for maximum likelihood. Let's extend it to the entire galaxy. Now, the age of our galaxy is about 13 billion years. That's very close to 13.8 billion years, about 800 million years after the formation of the universe. And it took about 10 billion years after that event for life to appear, about 3.8 billion years ago. Microbial life formed on Earth. We know that from very many sources, going from so-called stromatolites to deep ocean vents and other cores of the prehistoric fossil record, if you will, of bacteria. So now we're going to use capital P for the probability of life emerging per year on a suitable planet. And therefore, the probability of life appearing in 1 year is lowercase p. Now, the probability of no life is just 1 minus that, or 100% minus this probability. For Earth to be first, no life appeared anywhere else before life appeared on Earth. Now, for the t years before Earth's life, the probability at which Earth would be first is 1 minus p to the n times t power, where n, capital N, is the number of potentially habitable worlds that existed before life existed on Earth. So T here is about 9.2 billion years. It's the time between the Milky Way's formation and Earth's life formation. N is approximately 40 billion rocky planets and maybe giant moons, and that's a conservative estimate. Could be 10 to 100 times bigger for our galaxy. Now, we know this probability must be greater than 0 since it happened here. Therefore, we get a lower bound. The probability has to be greater than, so 1 minus p to the 40 billion times 9.2 billion years, this must be greater than 0. Now, we can get some rough estimates in the spirit of Adam Frank's estimates for the number of planets, a billion trillion planets that he says exist in our entire universe, observable universe.
I'm just asking in general, about probabilities to make a technological civilization anywhere and at any time in the history of the universe. And that we were able to constrain.
So we get a number that if P is greater than 10 to the negative 21st power per year per planet, the probability of Earth being the first is vanishingly small. But if P is less than the same number, Earth could plausibly be the first life form. Now, given that life appeared on Earth within about 100 or 200 million years of conditions being right on Earth, having liquid water, not being too hot or too cold, not being bombarded by giant comets or asteroids, this suggests that P could be as large as 10 to the minus 8th, so a part in 100 million per year for suitable conditions. Now, you might be thinking this is good news, but it actually creates another Drakean-like paradox. If P is high enough to explain Earth, that is approximately 10 to the minus 8, Earth being first is incredibly unlikely. We have so many other planets in our galaxy alone. Now, if P is low enough for Earth to be first, life appearing so quickly on Earth becomes incredibly unlikely. And it's very hard for me, at least, to reconcile those two competing facts, that P looked like it's extremely high on Earth, but it looks like for Earth to be the only planet is extremely low probability, so it's incredibly unlikely.
We're not the first time this has happened. This has happened elsewhere over the course of cosmic history.
This tension, this paradox, like Olber's paradox, like Zeno's paradox, always suggests that either one of our assumptions is wrong, or 2, we're missing something fundamental about how life on Earth emerges, or 3, there's some observational bias that we haven't accounted for. How do we tie this back to Adam Frank's cosmic argument? Again, Adam claims that there's 10 billion trillion, so that the probability of life emerging only on Earth would have to be lower than a part in 10 to the billion trillion power.
10 billion trillion experiments.
Yeah, that's a lot of experiments.
That's a lot.
But always remember when Adam talks about this, and I did mention this with him when he was on my podcast, that's Adam's calculation and best estimate for how hard it would have to be for us to be the only life form in the entire universe.
Life is probably easy to make. That's my gut feeling.
That's over 13.8 billion years, and including over 100 billion galaxies. So I actually don't care about all those galaxies. We can't access them. Many of them don't even exist anymore. And we should really focus on the Milky Way galaxy and really devote that energy to the Milky Way galaxy, because that's the only galaxy we can actually plausibly communicate with. And actually, even that's too broad. We've only been sending out radio signals for about 75 years. That means that the number of stars within a region of space with a radius of 75 light years, that's the only kind of volume of space to have possibly received information about the Earth's existence. Now, how many planets are within this regime? We know confirmed exoplanets, that there's at least 200 confirmed exoplanets within 75 light years of Earth. Now, there are many, many more candidate totals, but the minimum number we know about is about 236. Let's go a little bit deeper and ask the question, how many stars are there roughly like our Sun, which is a G-type main sequence star, often called a yellow dwarf, even though I point out many times it's actually peaks at wavelength in the green regime. And we can look at how many stars are within this region, and we find a startlingly low number of about 25 Sun-like G-type stars. Now, if we include so-called F and K-type stars, which are slightly smaller and cooler and less luminous than the Sun, or F-type main sequence stars are slightly larger, hotter, and more luminous, these still, both types share some of the traits of the Sun. You get about 500 possible stars within 75 light years of the Earth. Now, if you have a hugely active star system, could you have life? Could you have a planet? Maybe, Betelgeuse. Red giant, could you have life? Yes, you could. But let's be conservative. And now let's multiply by a factor of 10. So if you have 500 G, F, and K type stars, and each one, let's call it that it has 10 Earth-like planets around it, although that's way over what most Kepler objects seem to be represented as, you get 5,000 planets within 75 light years of Earth. Now let's say they want to make a two-way communication, so we cut that by 8 in the number of stars, but you get around 500 planets or so. Not too far off from the number of confirmed Earth-like exoplanets in our nearby region of our galaxy. So this is a much smaller number than the billion trillion planets that exist in the history of the universe over its entire 90 billion light-year diameter. Okay? That's what Adam's talking about, for us to be the only ones in the entire history of the universe. I don't care about that.
I don't care!
I really care about stars that are close to us and exoplanets that are like the Earth and stars like the Sun itself, just because we know for a fact that we exist. We don't know for a fact that any other life forms exist. Now, maybe it's biased, and maybe we'll find life on Enceladus, which is not like the Earth, although it is rocky. It is orbiting a sun-like star, after all. So that probability that we discussed earlier, it could be much lower than the 15% that we estimate. It could be like a part in 1,000. But Adam's stance is that we shouldn't assume an extremely low P until we gather more evidence, especially given how quickly life emerged on Earth once conditions stabilized.
If my team, the group I work with, if one of them says, look, wants to announce that, we've discovered a technosignature on an alien planet, we're going to get shredded, as we expect to be. So that's where I am right now. I just don't think any of the evidence is even close to anything that could support that claim.
Moreover, if we detect a second origin of life within our own solar system, we'll talk about that next, that would strongly suggest that P is not vanishingly small. For example, if we stumble upon microbes under Europa's ice or found fossilized microbes in a Martian lake bed, it would revolutionize our cosmic perspective on the fecundity of life. This is precisely why Adam argues that the next few decades of exoplanet spectroscopy with Webb and the Future Habitable Worlds Observatory and in situ exploration on Mars and the outer icy moons by instruments like JUICE and Europa Clipper, they might be game-changing for astrobiology. Now, let's beef up this Bayesian idea. Let's consider the different worlds within our solar system. Let's think more locally rather than globally. There are 4 major candidates that people talk about. Again, I'm a cosmologist. If I get these wrong, give me some latitude, give me some inaccuracy leeway, but I'm kind of laying it out as a physicist would. Kind of do these back-of-the-envelope calculations, back of the napkin. So let's look at those 4 worlds: Mars, Europa, Enceladus, and Titan. The latter 3 are moons, and Mars, of course, is a planet. Let's say each has a probability of p, lowercase p again, of hosting currently or having once hosted life. So the chance that none of them do would be 1 minus p to the 4th power. Hence, the probability that at least one does is 100% minus that number. So even for a small p, you factor in multiple shots, that probability can rise significantly. And in the Lex Friedman interview, Adam points out that we already have 4 or more potential habitats just in our local system, making him hugely skeptical that Earth is singularly unique, though he acknowledges the challenges of verifying life in each of these environments.
You actually have to think hard about the planetary context for life. You can't just be like, oh, there's a warm pond, and then some interesting, chemistry happens in the warm pond. You actually have to think about the planet as a whole and what it's gone through in order to really understand whether a planet is a good place for life or not.
Now, we have 0 evidence of those. And in one of those we've already been to and rove over it, and that's, of course, Mars. So Mars is the most perfect laboratory we know. I already said it's the most Earth-like of non-Earth planets. It's the closest example of a candidate world, and it has a special tie-in with conversations that we've had about so-called panspermia. Now, this is the concept that since Earth has had microbial life for billions of years, large impacts by meteors, like this one that you get if you're a lucky winner each month at briankeating.com/list, or if you're guaranteed to win one, if you have a .edu email address, go to briankeating.com/edu to win one of these beauties for sure if you live in the US. So if these impact Earth while Earth had a ton of life on it, literally tons and tons of life on it, over enough eons, enough material could have arrived to seed a second biosphere on Mars as well. Now here I have an object, a meteorite, which I will not give away because it's simply too expensive. I have a piece of Martian meteorite. I gave one to Joe Rogan. I gave one to Stephen Bartlett. I don't know what they did with them. But these meteorites have come from Mars, in this case by an asteroid slamming into the surface of Mars, ejecting the material. Eventually it made its way to Earth. So it could have seeded life on Earth if there was material on Mars in microbial fashion. This is only a few years old, this particular one. Found a few years ago from a fall, but it has all the characteristics of being on Mars. But let's go the other way. Again, we're trying to see how easy or hard it is for life to spread. This is called panspermia. Sounds dirty? Not dirty. So over the billions of years in which Earth has had life, especially during the period of time in which Mars had liquid water on its surface, some fraction of bacteria-laden rocks or microbial life-laden rocks ended up on Mars. Over eons, enough might have arrived there to seed that biosphere. The reasoning is that if panspermia were truly easy, we might expect to see robust evidence of a second genesis on Mars by now, but we don't. So far, that sets an upper limit on how efficient panspermia could be or how likely it is that any microbe can endure all the hazards en route. Let's look at the detailed math behind that. The first element of panspermic calculation involves the impact ejections and transfer fractions. So how many ejection events occur over the 3 to 4 billion years on Earth in which it experienced hundreds of major collisions? Let's call that number capital N. We don't know what N is. We can look at the moon to see how close we dodge bullets of a given size. But let's set that N to a rough figure, say 100 to 200. Now, how much schmutz, how much mass gets ejected per event? Let's call that capital M. Each large impact might eject on the order of 10 to the 11th or 10 to the 12th, a trillion kilograms of material. The fraction that escapes Earth's orbit is smaller, but let's denote that capital M as the mass that actually enters the interplanetary trajectory that ends up on a highway in space that ends up on Mars. Now, what fraction reaches Mars? Let's call that P sub transfer. Orbital mechanics studies often suggest around 0.1% to 1% of Earth-ejected schmutz might eventually collide and land on Mars or collide with Mars's atmosphere. Let's not talk about landing just yet because Mars also has explosive meteor detonations in its atmosphere, although it's much less dense than the Earth's atmosphere. So that's higher probability of landing on the surface. But the first element we have to calculate is what's the probability for the transfer to take place. On the lower end, it might be suggested as low as 0.001, so 0.1%, and it might be as large as 1%, depending on assumptions. But again, we want to have a range, and then we can fill in and you can adjust and dial in this type of Drake equation for the transfer of life from Earth to Mars. You can fill in your favorite values. I'll illustrate how to do it. So the total mass that impacts Mars's atmosphere is capital N times capital M times P sub transfer. Now, over billions of years, you get a time average flux of the schmutz from anywhere under a kilogram per year up to tens or hundreds of kilograms per year, depending on the scenario. Now, there are large uncertainties in this. It's very hard to actually calculate it, but there's a non-trivial amount of Earth material, most likely on Mars as we speak, and has been going so every year for the past 3 to 4 billion years, which these two sister planets have shared roughly the habitable zone orbits that they now enjoy. Now, the next step is how much microbial life survives. Just impacting the Martian atmosphere is not enough to assume that it survives to land on Mars' surface. Remember, we want it to seed life, like you're spraying Mars with life, during a period of time in which it's fertile, and that means it has to have liquid water. So the survival probability for any single microbe that can endure the shock, the vacuum of space, and cosmic ray radiation as it voyages from Earth to Mars, then survive re-entry and landing, may be extremely tiny. Typically, estimates could be as large as 10 to the minus 5, so a part in 100,000, and as small as about 1 part in a billion. But when you start with trillions of these microscopic microbes, even a meager fraction can mean billions could remain viable upon arrival. Next, there's a effect that we call the founder effect, and it's the hurdle of whether or not these billions of arrivals, distributed over millions of years, can gather in the same place, time, and under the same suitable conditions to then take hold and start to seed life on Mars. Now, Mars's habitability is believed to have peaked in the Noachian period, which I wasn't aware of until I did a little bit deeper research, and that's about 3.5 to 4 billion years ago. Now that roughly overlaps with Earth's earliest biosphere. So if watery crater lakes existed or geothermal regions persisted, that's the target zone. But if the microbes land sporadically at the poles, some over here, a patch over there, in places that never had sustainable water, you fail to establish a lasting biosphere. This is very simple modeling, but again, I'm highlighting some of these effects to illustrate the maximum and minimum probabilities that this panspermia effect occurred. This founder effect is crucial. You might need 1 million or 10 million microbes in the same microenvironment, the same culture. Imagine these microbes starting a disco and a supermarket and all sorts of things. That had to happen within a short time scale to overcome the lethal factors that then would lead to not establishing a stable colony. If they get spread out too thinly, life never gets a chance. Life would never find a way.
Life, finds a way.
Wrong, sir. Wrong.
That might be a big part of why Mars is currently lifeless, or at least seemingly so. Panspermia alone wasn't quite enough. So let's do a quantitative example, assuming a 500 million year overlap of fecundity on Mars and fecundity on Earth. So let's look at a specific scenario, the kind that's reminiscent of what Adam loves to do and does so uniquely well. So this overlap period of about 3.5 to 3 billion years ago, when Earth had microbes and Mars had surface water. Let's assume there were 20 big ejections from Earth during that 500 million life year span. Let's assume each ejection had 100 billion kilograms above the Earth's escape velocity. Let's assume 10 million cells per kilogram, microbial cells, which is roughly representative for near subsurface rocks on Earth at least. Let's assume the transfer fraction's about 0.5%, P sub transfer is about 0.005. And let's assume the survival fraction, P survival, is about 1 in 10 million, 10 to the minus 7. So the total amount of special delivered microbes from Earth to Mars is about 10 billion microbes in this scenario. This is a very rough but fairly conservative estimate that these 10 billion microbes arrived over 500 million years. A very large number, you would think, 10 billion.
That's a lot.
But is it enough? I don't think so. If Mars had thousands of crater lakes or micro-niches, each needing 1 million microbes at once, we may just be at the threshold. Some simulations would succeed and some would fail. So it's not guaranteed recipe for a second biosphere. And of course, if they landed at the poles or there was no liquid surface water of Mars, just like there's no liquid surface water at the North Pole. So I've been to the South Pole. There's no real life there besides the human variety. Again, this is very conservative, but we're trying to tie it back to the conversation between Lex and Adam. They debated whether or not life in general might be abundant in the universe, while acknowledging that civilizations that were advanced and long-lived could be extremely rare, much rarer than this panspermia calculation suggests.
The hard steps model, which is this model that's been out there for a long time that purports to say intelligent life in the universe will be really rare.
Now, our calculation hints at a fact that although Earth has had many opportunities to seed Mars, we're not seeing robust evidence of success there. Now, that might point to life's fragility, or it could point to the stringent requirements for establishing a stable foothold, or we might find life tomorrow, and I'm completely wrong about this calculation. But to date, we don't have any evidence. And typically the argument is, as Carl Sagan gave in Contact, if the universe is so capacious, so roomy, and so potentially habitable, why would we be alone? But that's a specious argument. As I said, also going back to my time in Antarctica, Antarctica is about 8% of the land surface of the Earth, and yet it has 0% to very good approximation of Earth's biodiversity, of biosphere. So you'd think if all things are being equal, if space is all you need, then it should have about approximate amount of life, 8% of life, and it has 0%, to round to the nearest digit. So the question that Adam and Lex get into are intelligence and planetary intelligences.
Intelligent life and how long technological civilizations. I think there's a big question about how long those last and how, I'm hopeful. I think life is absolutely going to be common.
I think that's kind of speculative. If life didn't exist on Mars, maybe it's never reached a higher threshold to go anywhere else. And so talking about life on other planets that become technological is a fool's errand in a sense, because if you don't have microbial life, it's very hard to imagine you get much, much higher multicellular organized life. Again, not a proof, but a suggestion. So the conversation that they discussed both hint at how JWST and eventually the Habitable Worlds Observatory could definitively tell us if we're an anomaly or just one cosmic data point among countless living worlds. Now, as Arthur C. Clarke said, the name of this podcast said, the only way to determine the limits of the possible is to go beyond them, into the impossible. As he also said, there are two possibilities. We're alone in the universe, or the universe is teeming with life, and both possibilities are equally terrifying. What do you think? If we discover no second life in our solar system, are these calculations about panspermia dead as a doornail, dead as the moon surface is? I really love the conversation that Adam and Lex had to have these numeric estimates, probabilistic thinking, taking into account uncertainties, what we don't know. And Adam says that and highlights that so often. It's so nice to hear these conversations and do them so uniquely well as Lex is solely capable of doing.
Thank you for talking today.
Oh, thank you. This was a lot of fun.
So, to wrap up, if Mars shows no trace of life, it could either mean that the probability that I assumed earlier, 15% or as low as 1%, is actually way too high. And it could be much, much, much lower, if not actually zero. Now, even if life is common, the lifetimes of energy-consuming intensive species like us could be very short. Another way out of the Fermi paradox. So Adam argues that we need to treat these questions with rigorous mathematics, as he does extremely well in his papers. I'll have links to his papers down below. And that's what good science is all about. I hope you enjoyed how we can think about the probabilities of our uniqueness or lack thereof using tools of astrobiology, of geology, climate change, and Bayesian estimation. Whether P is large or small, I'm so glad that you're here. I'm so glad that you're not a rare fluke, my brilliant audience. And if you found this deep dive stimulating, I hope that you'll explore Adam's 2 interviews with me. I'll have links to them. And no matter what, we always have to remember our special perspective. We're the only life that we know exists. And even if we do discover life elsewhere in the universe, that won't diminish in any way our own uniqueness and special nature. Always keep exploring, and let me know what you thought about this type of deep dive, way out of my depth. I'm not in my lane here, so I expect to hear some of those comments. But I think some of these are common sense, and I'll show the resources and sources that I use down below. Thanks so much. See you next time.